So in this time, we're going to speak in English as yesterday, but also hablamos castellano en el campus, en català, si voleu. Pero bueno, benvinguts, benvingudes al segundo día de la Innovation Week. Como sabéis, es una iniciativa que arrancó el año pasado de la mano de Open Innovation Campus también, de la rama de innovación abierta de Telefónica. Y ahora, concretamente, como podéis ver, creía que estaba la otra slide, como podéis ver en la presentación, venimos para hablar de seguridad y privacidad en redes modernas de la mano de Eduard Marin Fabregas, que voy a permitirme leer la introducción para no dejarme nada de banda. Investigador científico en Telefónica Research, razón por la que estás también hoy aquí, del equipo que estuvimos ayer precisamente viendo de Nicolás, ¿no? Formas parte del mismo equipo. Y a su vez también eres profesor de la UOC, entre otras muchas, seguramente, papers, ponencias y colaboraciones que has hecho. Así que muchísimas gracias. Gracias por conectaros en el streaming a las personas que nos estáis siguiendo. Hablo así hacia arriba. ¿Qué tal vamos de energía? Ayer lo preguntaba, repetimos 4 de la tarde, ¿bien? Hay café, si alguien quiere por allí al fondo. Again, welcome, feel free, and the floor is yours.
Vale. I'm going to switch to English because I'm not very used to talk about this topic in Spanish or Catalan. So if you don't mind, I'll do my talk in English. So today, I'm here to talk to you about my passion. So I have many passions in life, but this is one of them. So this is about part of my research. So I want to talk to you about the security and privacy of networks, and I deliberately included this word next generation networks, which sort of implies that we need new ways to design, manage, and program networks, and this is what I want to talk to you about. And of course, these changes that we're going to make in these networks are going to affect the security and privacy that we can, the type of security and privacy attacks that we can have and the type of security and privacy solutions that we can build. I had a slide to talk about myself, but this has already been discussed, so I'm going to jump into the topic. So the first question is, why do we need to innovate in networking? No? So why do we need these next generation networks? Well, I mean, probably all of you are familiar with data center, clouds, right? I mean, we all use cloud providers. We also know of telecommunication networks. We know the type of new services that are being delivered through these telecommunication networks. And we also know that there are enterprise networks. Of course, all these networks may not be located in one single place, but there might be multiple sites that need to talk to each other, right? So here I added a picture of Google's network. So this is an internal network in Google. It's called B4, and it's basically a network that interconnects all the data centers, all the sites that Google has distributed around the world. Okay, so all these. So when you search something in Google, when you ask Google to do something, this is handled in one of these sites, but some of the requests that you make also require different sites to talk to each other. Okay, so it could perfectly be the case that one of your requests goes from one site to another, and it needs to go back or maybe leverage some services that are in one site but not in the other. Okay, so as you can see, it's complex. No? So you have a very large infrastructure, large network, different hardware, different services. You want more and more speed. Your services have more stringent requirements over time. And the network is key to provide all these services. So you want to find ways to manage it properly. And of course, you need programmability, right? Because everything is very dynamic, and this programmability will give you opportunities that you could not have if you didn't have programmability. But let me step back, and let me start a little bit from the beginning. No? So how were networks designed when they were first created? So typically, traditional IP networks are typically composed by 3 planes. And I will start from the bottom. There is the data plane, which is the sort of forwarding. So it includes the forwarding functionality. No, think of routers and switches. They are made to forward traffic. This is their main function. And the forwarding functionality could be seen as the data plane. Okay, But then we need to tell this router how to forward traffic. No? So we need a control plane. The control plane includes the set of protocols that we use to tell the data plane what to do and how to do it. No? But of course, we also need to be able to manage these devices. No? So the management plane includes all the services that we need to program, and I would say program between brackets because it's not really program, but manage these switches and routers remotely. Okay. Something that is very important, and I would like to highlight here, is that when networks were first created, all switches and routers have some sort of intelligence, right? So when we have routers and switches, they are to some extent intelligent. So if you remove one router from the network, the router has ways to, let's say, adapt, right, and find alternative path to be able to fix this issue that has originated in the network, right? So this was done on purpose. So one of the first goals of networks when they were first created was to have resilience. No? So what we wanted is that even if some routers and switches stop working, the devices themselves are clever enough to adapt and to continue providing the service. Okay? So this was the main, let's say, requirement that people who work on networking had in the early days. Okay? This is, let's say, there's a clear justification on why they did this, and it made sense by then. No? But networks have also evolved, I would say, considerably. No? When networks were first created, they, I mean, think of the internet. No, there were only very few, let's say, places that had internet connection. They were all interconnected with each other, and now, of course, the internet is what it is, and there are additional properties that we would like to achieve, other than resilience. Okay, so take-home message: this was done for a good reason, but this also comes with problems. Okay, what are the main problems of doing this? I mean, as I told you, the routers now, well, routers before were, let's say, intelligent, okay? And this intelligence, what it means is that the data plane and the control plane are tightly coupled together in the router, okay? So this, I mean, as I said, has some advantages, but some disadvantages that I will now explain. And something else that I would also like to highlight here is that originally all these networking and these networking devices, it was all very hardware-centric, and it was also done through single-purpose devices. So we had devices that were very good at doing one very specific thing, and it was all based on the type of hardware that they had. No? So these routers typically rely on ASICs. ASICs is a sort of chip that allows you to send traffic at very high speed, but ASICs are very hard to reprogram. So with a CPU, you can reprogram things, but they don't offer so much speed. With an ASIC, you build the ASIC, you include the functionalities that you want in that ASIC, but once this ASIC is in the field, in the router, it's impossible to reconfigure it. So if you want to add additional functionalities, you basically need to create another ASIC. The problem is that this process of building these ASICs and putting them in place takes a very long time, and these ASICs are also very expensive. Okay? So it's not, let's say, something that you can do very frequently. So what are the consequences of these two problems? Well, that traditional IP networks were very complex to manage and control. So one of the problems was that to control and program the data plane devices, these manufacturers, let's say, they made available a set of commands that were very specific to each single device. Okay, so basically, to program these devices, you needed very specific manufacturer-specific device-specific commands that would only allow you to change very few things. Okay. So basically, what this meant is that you needed to have a lot of expertise in your team. You needed to know exactly how to program the different devices, and you also needed to have some, different, let's say, software to program every single device that you have in the network, okay? Another problem that there was is that it was very difficult to deal with faults and adapt to load changes. And these two problems that I mentioned before also hinder the innovation and evolution. So for example, to include a new functionality in one of these, in one of the routers, it was common that it would take a very long time. So it would take 5 to 10 years to design a new ASIC that included this very specific functionality. Let me just drink a little bit of water. Okay. So with this, I want to convince you that this hardware-centric and this hardware-centric design where the data plane and the control plane were tightly coupled together is not a good thing. So now we are transitioning from hardware-centric, static, very static networks to software-defined and highly programmable networks. And some of the technologies that I want to highlight to you is, for example, software-defined networking, which is the technology that we're going to talk about today with me. There is also network function virtualization, which basically means that you implement network functions in software, and instead of using specific hardware to perform certain functionalities, now you can move this functionality to the software that you can instantiate in different places of the network, depending on your needs. There is also work on programmable switches and through the P4 language. And this is something that Salvatore will be talking about later. There is also other very interesting technologies like containers and orchestrators. And basically these two can help us develop network functions in the network. Okay. So let me go a little bit more in depth on what SDN is. So software-defined networks, it's clearly not a new, I mean, I always like to say that it's not a new idea, okay? But it's a combination of very nice ideas put together. So there has been a lot of research on programmability. There has been a lot of research on separating or trying to separate the data plane from the control plane, but it never took off. I think that we were not ready for this to take off. So at the time where this was proposed, I think that these different research directions were already, I would say, mature enough. And basically some people in Stanford back in 2010 proposed this idea of, let's say, decoupling the control plane from the data plane, so moving away the intelligence from the router and centralizing this intelligence in an external entity. So I mean, imagine that we go from a situation where all routers have a sort of brain. We pull the brain from the routers and we put one single brain that controls all the routers. Okay? And the beauty of SDN was to have a standard API to program every single router, regardless of the manufacturer, regardless of the vendor. Okay? So instead of needing to think which vendor it is, which device it is, with SDN, you can program all the routers in your network without needing to know their, let's say, underlying details or anything about them. So it's a new abstraction. Okay. Another important aspect of SDN is that in SDN the forwarding decisions are flow-based and not destination-based. Okay, so this is one of the aspects that allows us to, let's say, extend the programmability that we have in the network. And another aspect that I also want to mention that you will see better in the next slide is that the network is programmable through software applications that run on top of this external entity. Okay. Ultimately, the goal of this technology is to be able to create more dynamic, agile, and programmable networks. You will see it better. I mean, I have a very good analogy that I think that you will all understand. Let me skip this one, go to this one first, and then I will go back to the previous, okay? So think about mainframes. So think about these old computers. So this is very old, no? These very tall and big computers that had very, I would say, specialized applications, specialized operating systems, specialized hardware, right? So this was back in the day. It's very old. What was the problem of this? Well, in this kind of solution, basically you need one company that knows how to do all of these things themselves, right? So how likely is it that you're very good in the hardware, that you're very good in the software, no? That you're very good at developing applications, no? So in this kind of setting, innovation is very complex, no? If you want to start innovating, there is a very, let's say, difficult market, no? I mean, entering as a new partner is very hard. And it's all very closed, very proprietary. No? I do it for me, and I don't want to let others do it. No? So I try to do it in a very protective way, which is generally, I mean, of course, for the company, might be a good thing and may give them an advantage, at least short term, but it's bad. No? And so now think about what has happened with computers. No? What we have on the right-hand side is what we have today. No? So we have companies dealing with the hardware. So that's the bottom of the image. Then we have different types of operating systems, right? I mean, I may have Linux, some of you may have Windows, some of you may have Mac, right? And then on top of these, there are apps, right? So I may use Firefox as a browser, you may use Chrome, right? And the beauty of this is that you can specialize on one of these layers, let's say. No? I mean, typically people doing operating systems, like companies doing operating systems don't do applications, and the same with the hardware and the software, right? Very few, if any, does software and hardware. No? So basically, this kind of design works amazingly well if there are open interfaces. So if I can very easily develop a new OS without needing to know everything about the underlying hardware or everything about the application. No? So if we agree on these open standard interfaces between the different layers, this model works very well. Okay, of course it facilitates innovation. It also encourages the industry, right? I mean, there will be people that will see this as an opportunity to innovate. And basically everything is based on these open and standard interfaces. So the same happens with the routers and the switches. So before, what I've been telling you until now is that we have routers that are very close, very proprietary, right? They have very specialized features. It's hard to know which features they have, or to really go deep on understanding how they work. It's very, very hard. Okay? They have a very specialized control plane, so specialized operating system, and they have also a very specialized hardware. Okay, so the same thing happens here. It's closed, proprietary, slow innovation, vertically integrated. What SDN suggests is go into what we have in the right-hand side, right? So we will have manufacturers doing the hardware, okay? And here the idea is that anyone doing a hardware switch could potentially be integrated here. Then we will have companies that will develop, let's say, operating systems for the switch, and this is the control plane, okay? But then, I mean, in such a model, we could even go further, and we could even allow different people, different, I don't know if I should call them developers, to develop applications, networking applications. And then each of us can take these devices and can use them in the way we want. No? I mean, I may use my router with ONOS instead of floodlight. Maybe some of you would make another choice. And maybe then on top of the operating system, I may use a specific firewall. You may use a specific intrusion detection system or anything similar to analyze traffic, right? And the beauty of this is that it all works very well because of these open and standard interfaces, right? Going back, this is the comparison between how traditional networks work compared to how SDN networks work. Okay, so in red you can see the control plane. Sorry, in blue you can see the data plane, and you can see that in the SDN case the control plane is, let's say, pulled from the routers, and it goes into a centralized place. Okay. I mean, don't think that this is a single point of failure. I mean, in practice, typically there are replicas of this SDN controller. So if someone wanted to attack this SDN controller, or if the SDN controller stopped working, there would be another SDN controller that takes over. Okay, but basically the point is this dash arrows from the SDN controller to the routers and the switches. This is what facilitates a little bit more programming in the network. Okay, and then you can also see the apps running on top. Okay, so something very important as well. No, so this is a project that started in the university. So as I said before, it was created in Stanford, but it has also gained quite a lot of popularity in industry. Okay, so I mean, you know all the companies that are here, but basically all of these companies have used or are still using SDN in their networks. Okay, so let me go a little bit deeper on how SDN works. No? So now, I mean, you should keep in mind that now the switches and the routers don't have any intelligence. They don't know what to do. Okay, so they need to be asking the controller for, let's say, instructions to know what to do with the traffic. No, so typically the way it works, and I had a nice animation, but with the PDF you cannot see it. I mean, if you pay attention only to the blue lines now, no, so we have some traffic coming to the router, and the router at first doesn't know what to do because it doesn't have any flow rules installed on it. What the router does is that it asks for instructions to the controller, and the controller pushes some rules to the switch that are cached. Okay, so these rules remain in the switch or the router for some time. Okay, so that the next time if packets of the same flow arrive to the switch or the router knows what to do. So the next time with the following packets, if you look at the orange line, the router won't need to ask the controller. It will take the rule that is installed already in the device, and it will forward the traffic directly. Okay. So now with this, I try to give you a very brief introduction to SDN. Let me talk to you a little bit more about the security of SDN. And I divided this slide basically in let's say, positives and negatives. No? So starting with the positives, one thing that I think is very positive in security in general, but even more when it's applied to networks, is that SDN is based on standard and open source initiatives. So everything or almost everything is open source, and therefore security experts can scrutinize for example, the different operating systems that have been proposed for SDN. With this centralized controller that has visibility on all the network, we have better visibility and better control. And this is typically something that is very good for security. In terms of the negative points, I would say that SDN has a larger attack surface. So it allows some level of programmability. I mean, remember that now you can plug SDN application running on top of the controller. These SDN applications could be developed by someone who's malicious. And all of a sudden, you would be running code that has been written by someone who's malicious in your network, right? So before, you didn't have programmability, which was bad, but you were not running this kind of third-party software in your network. At the same time, some attacks can be more severe. So before, for example, to do some attacks, you would need to convince every single router that something is happening. Now you just need to convince this external entity, this controller, this centralized controller. If you can trick the controller into thinking that something that is actually not happening is happening, the controller might be the perfect component to distribute this knowledge to the rest of the devices. Okay, so you need to convince one only. Another big problem is that there has been a lot of research on trying to secure these traditional IP networks, but not much, I would say, in general, there's not much that can be used, at least directly. Of course, there are some lessons learned from developing solutions for traditional IP networks, but in general, I would say that the change in mindset is so big that there's not much that can be reused, at least directly, okay, which is, yeah. And last but not least, there is this big problem that by default, SDN is not very secure. So even something very basic like having TLS between the SDN controller and the switches, which is basic, it's not enabled by default. Okay. So going a little bit into the research, but not going much into the details, there has been a lot of research during the last decade on SDN security. Some people have focused on finding new attacks. Okay, so for example, side channel attacks. Side channels basically tell us things that we should not know in ways that, let's say, are not direct ones. Okay, so I might be able to infer something about the network from, let's say, the way entities communicate with each other, the way the network deals with a certain type of event, right? I mean, remember that there is this change in behavior once the rules are cached in the router, right? So basically the time to transmit packet, one packet from one side to the other, when going through the blue arrows and going through the orange arrows is not the same, right? So there's an additional delay when we need to interact with the controller. And this, for example, is a very simple side channel that can give us additional insights on what is happening in the network. Okay, so we could know that a certain event has happened that has triggered the controller to install a rule on the device. There's a lot of research also on topology attacks, on trying to convince the controller that the topology, so trying to trick the controller into thinking that the topology is different, okay, to skip certain links, skip certain devices. There's also, I'm just going to skip some details, but there's also a lot of research on trying to automatically identify vulnerabilities in these SDN controllers. So in a sort of automatic way, so using techniques like fuzzing, trying to identify vulnerabilities that can be exploited by adversaries. And then there's another, I would say, set of works that try to propose defenses. No? And of course, there are also big challenges. So I want to tell you a little bit what my research is about. Okay, so my research, I would say, yeah. So for me, this area is a sort of sweet spot. So I studied telecommunications engineering. I did my PhD on security and privacy. So I have the sort of background to do this. It's an area that I feel very amazing. I mean, I think I would say that lots of things have happened that have changed the way networks function. It's also a very popular area, but at the same time, it's not overcrowded. So for me, this is a sort of sweet spot. And then in my research, I try to look at both the attacks and the defenses. I mean, I think that one without the other doesn't make much sense. No, I mean, if I want to propose a defense, I may also want to try to attack what is there. No, so in some of my work, we found vulnerabilities in SDN controllers, also in solutions that some other people have proposed. And what we try to do is always, let's say, with positive intentions, no? We try to improve the security by attacking, no? But we try not to stop on the attack, but also go beyond the attack and try to propose some improvements. Okay, and I do this in two different ways. No, I mean I try to see how the security of SDN is. So I try to investigate the security of the main building blocks of SDN. But then I also try to think about how SDN can help us secure against known attacks. Okay, I mean, I think that there's very interesting work on both areas. And just to conclude, I think that these are, I would say, very important messages. No, I mean, I think that network security is and will be extremely important. adversaries are always ahead. So even if you try to be better than them, they will always be better than you. And I think that to defend is extremely important to have a sort of adversary mindset. No? I mean, don't think about how things should work in theory. Try to find ways to make things work in a way that is not the intended one. No? And then a bit more centered on the talk, I would say, I think that programmability is great. It comes with great power, right? But it can open many, 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 many doors for attacks. But at the same time, the sort of positive message that I want to give here is that it can also help us develop much more, I would say, sophisticated security solutions against attacks. Okay, and I think that's all from my side. Thank you.
I think that we'll have, can I? Great. So I think, no worries. Thank you so much. I think that we'll have, wait, because I think that we have 5 minutes because we need to change some stuff with the computers with the next speaker. So I think that we have like 2 questions if you want to do to Eduard. We have time enough? Great. So I'm going to give you the microphone because if not, with the streaming, they won't hear anything. So.
Do you want a question in English or in Spanish? Okay. So you make a case for SDN, but you said that it has lower performance and lower security. So you are selling very valid the idea. I was thinking if you think of any case that is possible with SDN and is not possible with traditional, so any incentives to try to adopt these models.
Very fast.
Yeah, so worse security, yes, sure, not worse performance. I mean, one of the reasons why these companies that I mentioned there are using SDN is because they, for example, they can achieve almost 100% utilization on all the links. I mean, before, for example, Google had links that were congested and links that were not utilized almost. No? So one of the, let's say, killer applications of SDN in this kind of complex networks is that it can allow dealing with traffic inside your network in a better way. So it's certainly much better in terms of performance. Does this clarify your question? Well, I mean, I would motivate it in terms of, serving the network. I mean, suppose that you don't want links to be congested, right? If links are congested, the service that you're providing to your customers, you cannot provide it in the same way, right? So there are certain SLAs, let's say, that you can only sign if you use SDN. You can be more aggressive in the type of properties that you can sell. So basically, it allows you to manage the network in a way better compared to these more traditional IP networks.
Great, so thank you so much. Signorello, is it like that? Signorello? Yeah. How would you do it? How would you do it? Signorello. More or less. Anyway. Okay, perfect. So it's your turn. He's gonna talk with us about, as you can see there, what is network that are playing programming and why should we care about it? So the floor is yours. Thank you so much, Salvatore.
Thank you very much. Okay. Good afternoon, everyone, and thank you for attending. Thank you for your time. I'm Salvatore. I'm a research scientist at Telefónica Innovación Digital. I'm part of the same group of Eduard. It's a research group, small research group doing research at the intersection of networks, systems, and ML. You had the head of the group starting off this series of events on Monday, I think, with the very first talk was Nicolas. How many of you have heard about data plane programming before? I mean, before Eduard's talk, I mean, could you please raise your hand if you know, if you heard data plane before? No, okay, fine. So that's totally fine because this is the purpose of the talk. So my objective will be that I spark some interest about data plane programming, and at the end of the talk, you know, there are references at the end of this presentation, and if I got your interest, then you will go out and check the references and start learning something. And the objective is, I think data plane programming will become a relevant skill in a very near future. If you want to become a computer network engineer, for example, you know, it's going to be important that you know about some concepts like data plane programming. And I'm going to keep the, I prepare slides which are very high level, okay, on purpose. So I'm not going to talk in detail about specific projects we do at Telefónica or specific projects I'm working on and are of interest of me. But I want to give you some basic concepts about, you know, these technologies, okay? And I'll try to keep it 25-ish minutes. So also we'll have like 5 minutes for, you know, questions if you have any. Okay, more or less is going to be the outline of the talk, okay? I'm going to use, likely, you know, we didn't plan this much, but I'm going to use much of the content also that Eduard gave. I'll go a bit more deeper into some basic concepts, fundamental things. And also I look, it's interesting because I look at the problem and opportunity also from a different angle, I think. So we'll recap very quickly basic concepts of computer networks. Then we will see how networks have become programmable up to today. I will talk very quickly, you know, this is a school, I know this is a school, you know, where you learn to program things, you know, I'm going to disappoint you because there's going to be only one slide with some code of it, okay? And we will see a language and tools from programming the network data plane, and some examples of very cool innovation that programmable networks and languages like these allow to achieve. And in the end, I'm going to share my view of things that will happen in future networks. And I also take the chance to say this is my personal view, neither the one of the company nor the one of my team, I think, except a few people in, okay? So let's start with the network layer. Okay, if you have ever taken like an undergraduate introductory course on computer networks, probably you know this book. It's a very famous book, you know, written by those two professors, Kuros and Rose, which, you know, this is in use by hundreds of universities and colleges worldwide and translated, I think, in anything between 14, 15, 16 different languages. And if you know the book, you also know that basically it has a top-down approach. So basically they go layer by layer over a set of protocols we use in the internet, right? And if you were as unfortunate as I was when I took this course, basically, it's a very boring one. You know, many teachers fail to give a much broader view about networks, okay? So basically, they explain you a very boring list of protocols, okay? And just, you know, to back up this claim, which is very strong, you know, this is also the vision shared by many, you know, important researchers, for example, worldwide. So some of the, if we look at network, and you are familiar with this stack of protocols, this is actually what the book goes into explaining, okay? So they start from an application layer, and they take a top-down approach from the application layer down to the physical layer. And layer by layer, they explain you protocols that used to communicate, the devices used to communicate in the network, used to communicate through the network. At the thin waist of this hourglass structure, you got a protocol, which is IP. Everyone is familiar with the internet protocol, okay? It's something very simple, but it's extremely pervasive. So you have it on every device in the internet. So if you wanted to communicate with any other device on the internet, basically your device will talk that protocol. So you have it on end hosts, on your phone, on your computers, but you have it on every single device that forwards traffic in the internet. And it offers, let's say, two main services, okay? One is forwarding. So I'm on a single device, I'm getting a network packet on one of my ports, and I need to decide how to forward this out of some of my ports, okay? So it's a single decision on a packet. It's in, how do I put it out? Where exactly I put it out? And the other one is routing, okay? So I have a source and destination. I have two computers that want to talk through the network, okay? How do I know which path they should take to get from source A to destination B? And probably, in most of the cases, usually when you take such a course on computer networks, you know, those are the things you learn about IP, okay? So they don't go much farther. But I'm gonna highlight a few different, let's say, perspectives at the network level, which are the following, which is the division between two separate logical planes that you have in the network layer. For example, in a protocol like IP. As you've seen in the previous slide, basically forwarding is an operation which is local to a single device, okay? And if you look at the other one, which is routing, it's more from a source to a destination. So basically this encompasses different devices. So there's a logical difference there. One is per device, one is network-wide. And if you look also at the top of the slide, you'll see that a blue block is inside every single device. As Edward was saying, basically, there is some control plane logic in each and every device as well, okay? And those logical planes have different requirements. One is meant at very high speed to take packets and make forwarding, you know, take forwarding decisions. The other one, a bit slower, you know, has to decide which are the routes from sources to destinations, okay? When I get a packet which has a certain destination address, how do I forward it out of a certain device so that it can reach at the end, you know, a destination? So they have different requirements. Let's go a bit deeper, you know, to give you an example with IP. Basically, the data plane is exactly where you take forwarding decisions. So you may get a network packet, you analyze the packet, you analyze the protocols inside the packet, you extract some fields, which could be an IP destination address. But the control plane is the one who decides the effective rule that you want to apply to a certain packet. So, you know, the address, you know, the output port. So they sit at a different, you know, logical level. So you may have already guessed what data plane programming is exactly reconfiguring, you know, the logic that you apply at the data plane. So in this case was forwarding logic, you know, in most of the cases we know about is how do I decide based on some packet fields how to process a certain packet, you know, in this case could be the address. But, you know, there are a bit more operations that you can perform on packets. You know, you can identify many more protocols than IP. You can modify some of the fields inside packets for specific purposes. You can do classification. You can filter. There are more operations, you know, in addition to the forwarding one. Okay, so you say, why should I care? Okay. This is actually very interesting because as Edward tried to tell you, like in this presentation, you know, you may think, okay, it's easy, you know, I'm gonna write my custom packet processing logic, you know, and I'm gonna run this on my device. Well, it hasn't been the case for a very long time, okay? So devices haven't always been so deeply programmable. To explain you why this is important, I will pose a question, which is, you know, who really owns control of the network, okay? Assuming I operate a network, you know, I have a set of those devices, okay? What is my freedom, you know, to manage and implement services on this network? Well, let's go through different cases and see which are the options you have, okay? I would sort of argue that, you know, if you can program it, if you can program entirely the device, of course, you have sort of control on it. If you can't, well, you know, that's a bit different. And this is extremely important because basically once you can decide what software to run on the hardware you own, you decide what to do with it, okay? So we'll try to get to this situation where you can really program the devices that operate in your network, that you put in your managing your network. Okay, and we will start with a case that Eduard was explaining to you, which was, these devices, specifically in certain segments of the network because of performance requirements and also because of market interests, they were designed in a certain way. So you had, let's call this vertically integrated solution when everything was basically together, software and hardware built sometimes from the same big company, okay? In this case, the question, who really owns control of the network, I mean, if you have a network full of these devices, who owns control is basically the company, who manufactured the chip, and wrote the software that ran on the devices. Not much of freedom there, right? So, but we need to get to that case, we start from everything is closed proprietary, I don't see the software, I don't write the software, to a case where, I can possibly write my own packet processing logic. So what is blocking us, or what blocked us for a very long time to get there? There were, I would say, at least two different sort of barriers. One was, let's say, a market-driven one, okay? Big companies, big vendors used to hold control of these devices, of course. They had a huge interest in being the few ones worldwide that could write and manufacture and write software for these devices. And then, SDN was proposed. Now, I'm summarizing only one principle. As Eduard showed this in the presentation, this was proposing many more things. But one was, of course, the separation between control and data plane. At least, allow the people that, buy, for example, networking devices to be able to write their own control plane software, okay? So basically, turning the control plane from red to green and also opening the interface between the two planes, okay? So I have some sort of, I can program the control plane and I know how to talk to the data plane. Okay. And again, the question, who really owns control of the network now? Okay. Well, if you think about it, it's true that you can write your control plane software, but you still are limited to what's in that chip. So who's gonna manufacture your, for example, switching ASIC decides the functionality that the hardware will implement. So you are somehow limited still. Okay. And this is basically the second barrier, which is a bit more a technological one. Okay. For a very long time, it was believed in industry, but at least, maybe it wasn't entirely believed, but, some big stakeholders took advantage that, the large majority of people believed it wasn't possible to build fully programmable, high-speed packet processors, the chip you see there, for a very long time it was believed that in order to process millions of packets per second, so in cope with very high-speed network links, wasn't possible to have a chip that you could program and reconfigure based on the protocols you want to run it, okay? So you had to decide your protocols, add design time, and then manufacture a chip that, will be able to understand only a limited set of protocols. So you could process packets very fast and very efficiently. Okay. But then some researchers proved that it was possible to indeed design a chip for networking that can be reconfigured, okay? With some limitations. It's not a general purpose CPU, okay? But I can still write a chip for networking purposes that offers a very good degree of programmability. And this is quite an inflection point Because if you think about it, if before it took several years of agreement and design in order to get a chip that could speak a certain protocol, okay? There are cases where from the invention or design of a novel, very simple protocol to have this supported by devices on the market, it took like 4 or 5 years. Because before there is a standardization process between different big players, and once they decide that the protocol is good enough, it goes in production into a chip. And producing a chip with this very nanotechnology is a very long and expensive process. So let's say people think it, many, many times before entering this production. It's a very expensive and lengthy process. Okay, but now assume you have it. And basically now this is commercially available, okay? So you can write your control plane software, okay? And you can also, you can really specify at the lowest level the sort of operations you want to apply to traffic, network traffic. So you can write both, okay? So if I ask you now again, who owns control of the network? Okay, I would argue, of course, this is a oversimplification, but I would argue that, you've got much more control if you operate a network where you have those devices. Okay, this comes, of course, with some constraints. So, recapping a little bit. So we moved from a very bad, let's say, state of affairs where everything was proprietary and closed, then partially open, okay? And now we are heading towards a scenario where everything will be open and programmable, I mean, if you will, okay? And if you see also the title of the slide, things have changed. So I say from bottom up to top down, because before it was basically the hardware deciding which sort of functionality you could implement on networking devices. Now, if you write software, you can push it down to the lowest level and decide exactly what the devices do, of course, within the limits of what a chip offers. Okay. So now we have got there. How we program the data plane, okay? How people program the data plane. Well, this is may sound like a very basic question. Of course, you may think, okay, I have a language, I will have some software that translates this language. I mean, the answer is not so straightforward because when everything was closed, people mostly use their own, low-level languages to program their own solutions. For example, it was Cisco, I had my router, I would write my, let's say, micro-level C code for my specific device. And then I would write my operating system for the device in another language, and everything was my own decision, okay? If I make an analogy with the CPU market, okay? Maybe not many of you are old as I am, but now there are other high-level programming languages, but usually what's the beauty of programming in a language and put it across different platforms? That basically you have this high-level universal language that you can write programming logic, and then you'll get dedicated software that will translate this, will deal with the intricacy of each hardware platform, and would translate this into low-level, binary code that each different processor would understand. Okay. Okay, so you may think, okay, this is a good approach. Why is it not there? For the reasons I mentioned before. Okay. There was no coordinated effort towards the design of such language. Everyone was implementing his own solution for their products. So there are indeed different platforms you that offer data plane functionalities you could program. But, indeed, there are, I mean, now we have some of them, but they didn't used to have a specific language for data plane programming, an universal one, I would say, and a set of compilers that could translate this language into machine-level code that any of those devices could understand. Okay, so let's think about how would we design such a language, okay? There are at least, I would say, 3 properties that you may have guessed yourself during the presentation, which is, okay, I don't want a language, okay, we are going to design a language which is for packet processing tasks, so it's going to be very different from, you know, high-level languages you may daily use, like C, Python, Java, whatever. So this is meant to operate on packets, on network traffic. But you don't want this to be protocol independent, okay? I don't want a language that allows me to program, you know, IP processing, because, you know, I would like to try a different protocol, which is not IP, or which looks like different from IP. And also, I don't want a language which is target dependent, okay? So otherwise, we go back to the solution where every vendor was implementing his own, you know, low-level language for his own, you know, product. And things could be barely reused, okay? There were cases where the same company moving from one generation of devices to the next one would need to re-engineer, again, you know, the operating system of, you know, a router, okay? Because it wasn't portable. And I will add one more, which is the language must have a fundamental property, which is must be expressive enough, okay? That doesn't constrain you to only a limited set of functionality. Okay, and now we reach, let's say, the core of this presentation, which is P4, okay? Which is a language for data plane programming. This language has been proposed quite recently, okay? It has been late 2013, became 2014, 2015, the first specification went out. It's a community-driven, the design of this language is driven by the community. Started with a few small set of academics and industry players, but then has reached many more, you know, stakeholders. The P4 comes from the original proposal for this language, which was programming protocol-independent packet processors, so 4 times P. I'm showing a very simple snippet of code, which has to do with a program that takes a packet from an input port, you know, and forward it out of another port, okay? And the core of the language is based on abstraction, which are tables. And this is very common when you process packet. You look at certain fields into the packet, you know, you apply a table and decide what to do. I change a field, I rewrite another packet field, like a destination, MAC, you know, and I forward it out. So the core language syntax is very simple, you know, and allows you to do things that you usually do with packets, okay? For example, match action, defining protocol headers, parsing, so identify the protocol in your packet, then defining your own variables and the variables of a target you are programming, applying some logic. And the very last one is very important because it gives you a hint about the programming model. I'm importing something which is specific of a target. How does it work programming in P4? The core syntax, okay, if I go back to this slide, the core syntax, which is included at the beginning of this file, is very minimal. It's a very minimalistic language, okay? But still very powerful in the sense that it allows you to express different behaviors. And how does it work? So P4, basically, it works, it's based on the programming model on a separation of target architectures and P4 programs. So you're going to write your packet processing program in the core syntax of the language, and you will leverage for specific purpose, you know, target specific, you know, engines or features of your hardware. And you will compile it. Some pieces of this compiler, maybe, you know, probably the highest layer of the compiler will be generic, and the lowest layer of the compiler will be target specific, as in any other case. Okay. Let me also walk you through 3 examples why the ability to program the data plane is very important for innovation. Okay? I try to touch different areas just to give you an idea of the sort of things this change from not having devices in the middle of the network programmables to having them, what can bring, which sort of advantage. So if before, I love a lot of animations, okay? So, sorry if this is full, but basically before, if you had to do any monitoring task, okay, you'll probably, devices in the middle couldn't be exactly programmed for a specific task, so you would use what the vendor would offer you. And for example, you would steer all the traffic, the simple traffic, to your monitor infrastructure, and draw conclusions. Okay. But what if devices in the middle were programmable, okay? Like this, a little block in each one. And the block can be whatever, So you can monitor traffic information and, of different sorts in different ways, okay? But the mind-blowing shift is basically that now, once you carry traffic in between the network, you can essentially collect that information, okay? And again, send it somewhere, okay? And this would give you much more visibility of what is happening inside it before you didn't have, okay? And this has been a very, broad summary of something that people maybe call, in-band network telemetry. So how can I extract, measurements from the networks that I can use for network analytics, for example, and allows you, many the design of many important monitoring solutions, okay? How much time? 3, okay. Another case is the following. Again, devices in the middle, used to not be fully programmable, okay? So assume they will speak IP, there's a Chinese sign there, but if you had to devise any other new protocol, what you could do is basically you could implement this logic at the end hosts. I would design my protocol A, I would implement software on my end host, could be computers and then servers, but in the middle, the routers wouldn't have visibility, okay? But now, assume that this is gone, and basically up to certain limits, devices in the middle can talk, it can understand, can be programmed to understand different protocols, okay? And this again enables a wide set of different, applications. You can think of having very fast response to routing problems, for example. You can use the network to build better congestion control mechanisms, etc. And the last, which I'm very passionate about, I do a lot of research on this, is basically leveraging the network, as support for defense. Okay, we traditionally, I would say, we will put defenses very close to the attack victims, okay? But now, sort of, you can think that these devices can be programmed, okay? So you can move and instrument defense where you like. And this is the advantage that basically, you can detect, for example, attacks much closer to the source. You can devise much more effective countermeasures and a set of other, applications. Okay, just to give you a glimpse. And I would say I would pitch at least 2 scenarios that I think will happen in the near futures, which are the following. One is basically this whole data plane, the design of a data plane language started with the emergence of programmable switches. Okay. But now, people also, thanks to this effort, started to rethink packet processing logic, in other places, like in software stack in end hosts, okay? So this could be in, for example, software stack you have in the kernel of your operating system, or in the virtual switch of your virtualization environment, or in the smart NIC you have in one of your servers, okay? And so ideally, basically, you can have an application and partition, decide which part of this networking program will go best on which target. bit visionary, but there are efforts going in this direction. And the other one is the following. You may have a network which is programmed through this data plane programming language, and a set of compilers and platform which allow you to do so. And you can collect your custom measurements, for example. And thanks to this visibility into the network, you may also decide to react autonomously. So you may think that the network you can program the network fully to collect these measurements, also put some logic there that can analyze these measurements and eventually, change the program it's running to react to some events, And there are already research projects on that. Okay. So I'll conclude telling you, I hope that you leave this presentation with at least some curiosity. You go out, there's a list of references at the end of the slides. I don't know if they share the slides, go wild, and learn more about data plane programming. Thank you for your attention, guys.
Thank you so much. I think that before we jump into the last part of the day, we have 5 minutes for questions. Do you want to have? Yeah, great.
Aren't smart net? Sí. Está muy bien. Isn't Cloudflare, for example, known for applying smart rules on their network security? For example, they say that a lot, actually.
Yeah, okay. It depends on where you want to apply these, let's say, let's call them rules, okay? If you have an infrastructure that allows you to apply these things in software, and you don't worry about delaying the processing of your network traffic, you do not even need such a technology, okay? So it really depends. Think there are a lot of work in data plane programming went into, for example, data center networking, okay? Which is handling, large amount of network traffic at high speeds, okay? In that case, you don't want to delay the processing of a single packet so long, and so sometimes you want to apply a decision or an entry or a rule, as you call it, in hardware. So I'm not aware of Cloudflare itself, but there are companies like, I can tell you, Alibaba, for example, which is another cloud provider, does it. I'm not aware of work done by Cloudflare in the area of data plane programming. It doesn't mean that they don't do it, just me. Yeah.
No? Okay, so thank you so much. Big applause. Ooh. Yeah. Great. And then the last part of the afternoon will be with a workshop, a hands-on workshop that we'll have with Birup. Your surname is quite difficult for me to spell it. Ramajiri also. I should learn more languages. But that part of the day won't be through streaming. So we will cut the streaming right now. Thank you so much for those who are at home. Perdón, y yo sigo con el inglés, ¿no? Cambiamos, como estaba diciendo, muchísimas gracias para las personas que estáis siguiéndonos por streaming y para las que continuamos por aquí, pues tendremos ahora un fantástico taller de automatización de procesos, entre otras muchas cosas con la robótica, así que a aprender muchísimo y gracias de nuevo a los dos ponentes, ha sido un gustazo, Eduard, Nico, muchísimas gracias. Y seguimos, so sorry, de hecho, efectivamente.